Okay, so we continue with this course. We will now be talking about four vectors. Maybe you know a little bit of four vectors from last year, but in this course we will see four vectors in a lot more details. So let's begin with a little comparison with a 3D vector. You know that in a normal space and in a Euclidean space, a 3D vector is simply the distance between 2 points of the space, but this distance is defined by a certain line and a certain direction. So you say that you go from point A to point B, or from point B to point A, which is a straight line between the 2 points defined by a certain direction. And you give to this 3D vector 3 coordinates according to the 3 axes of coordinates, x, y, and z. So you have 3 components or 3 coordinates of the vector. This is in a 3D space, in a Euclidean space. So we will use a new notation now. Instead of putting x, y, and z as the 3 coordinates, we will note them as xr. So I is going from 1 to 3. So the coordinate x is x1, the coordinate y is x2, the coordinate z is x3. So instead of writing x, y, and z, we will make it as x1, x2, x3. So x, which is the first coordinate, is given as x1, and etc. for y and z. And here 1, 2, and 3 are indices, so don't confuse it with a power. So x2 is x number 2, x index 2, not x squared. Why do I put them as a superscript? I will tell you at the end of this chapter when I will explain the difference between covariant and contravariant coordinates. So for now, let's just write it as it is, the index as an upper, as a superscript index. So an upper index instead of a lower index. So x1, x2, and x3 are the coordinates in space as x, y, and z. Now, if you go to space-time, so in a 4-dimensional space, you have a 4th dimension, which is time, as we explained in previous videos. So now you have x, y, z, and t. Now, the standard notation in special theory of relativity is to put them in this order as x index mu, as t, x, y, and z. And mu is an index that goes from 0 to 3. Because historically, x has been considered always as the number 1 coordinate. So we will keep x as the number 1 coordinate, and we will consider 0 as the 0th coordinate. So in a 4-vector notation, x mu, the 4 coordinates of a 4-vector, are written as x0 instead of t, and x1 instead of x, x2 instead of y, and x3 instead of z. So you have a set of 4 coordinates, 0, 1, 2, 3, and the x0, the 0th coordinate, corresponds to the time axis. In some older references, they consider t as the 4th coordinate. They consider time as the 4th coordinate, and they tell you that mu goes from 1 to 4 instead from 0 to 3. So if you see it in some reference, it's the same. Old references use mu as 1 to 4. So x1 is x and x4 is t. But I think that now no one uses this notation. So now the standard notation is to go from 0 to 3 as considering time as a zeroth coordinate. So our proper time, which is the square of the proper time, you can call it proper time always, but it's the square of the proper time, which is t squared minus x squared. Now in a 4 vector notation, so we will put it as x0 squared instead of t squared minus x squared or minus x1 squared minus x2 squared minus x3 squared. So here you have the upper index 0, 1, 2, 3 squared. So maybe if you put a couple of parentheses here, you will see it better. So at the end, it's x0 squared minus xi squared. So also as a standard notation, I is used for the 3D space and goes from 1 to 3, and mu is used for the 4D space and goes from 0 to 3. So when you see the index I, it means you are working in space from 1 to 3, an Euclidean space, or with spatial coordinates x, y, and z. And when you see mu, it means that you are working in space-time in a 4D space, and you are using 0, 1, 2, 3, so 4 coordinates of space-time. So xi is the 3D vector, and x mu is the 4D vector, is a 4 vector in a 4-dimensional space. In order to build a 4 vector, the 4 coordinates of the 4 vectors should have a Lorentz transformation, should be able to be transformed by the Lorentz transformation. So it's not enough to say that you have 4 coordinates in a certain frame, you have 4 coordinates, then you have a 4 vector. No, in order to call it a 4 vector, your 4 coordinates should be able to be transformed by Lorentz. If one of the coordinates does not have a Lorentz transformation, then your vector is not a 4 vector. It is just a vector with 4 coordinates. In order to call it a 4 vector, the 4 coordinates have to be transformed by Lorentz. So we use the new notation. We use the new notation, the 4 vector notation, in the Lorentz transformation. So if you remember, the Lorentz transformation tells you that x prime is equal to x minus vt over radical 1 minus v squared. So x prime, the x is x1. So x prime is x1 prime, x is x1, and t is x0. So you will end up with this set of equations. x1 prime is equal to x1 minus vx0 over radical of 1 minus v squared. And the t is replaced by x0. So t prime is x0 prime, which is equal to x0 instead of t, minus vx1 instead of vx, over the radical of 1 minus v squared. So this is the new notation of the Lorentz transformation. This type of space is called Zaminkowski space, after the mathematician Hermann Minkowski, who was a mathematician who defined multi-dimensional spaces. So he was not a physicist, so he didn't really care about relativity and how to put four vectors and the special theory of relativity. He just defined spaces with n dimensions, and n could take any value from 0 to infinity. So you can define spaces into 4 dimensions, 10 dimensions, 1,000 dimension, any number of dimensions. But if you go back to physics, if you go back to reality, you know that you have 3 dimensions of space, x, y, and z, and you have as a time dimension, so you end up with 4 dimensions. So as if our space-time is a particular case, is a special case of a Minkowski space with n equal to 4. So we have a 4-dimensional space, a 4-dimensional Minkowski space. So the mathematics we are using in this type of spaces is the mathematics of Minkowski to define multi-dimensional spaces. So I always tell you the case when C is different from 1 in case you see it in a certain reference. So if C is different from 1, x0 would become a complex number, an imaginary number, and a complex number. So x0 is I, ct. I here is as you write it in a complex notation. Ct, so you give it a dimension of length in order to have 4 dimensions that are all or that have the dimension of length, because t is time, x, y, and z have the dimension of a length, and you cannot make a frame using a 1 dimension of time and 3 dimension of length. So the x0 is actually ct or ict. So when c is equal to 1, you don't care about this. Ct, when you multiply the time by a velocity or by a speed, your final dimension is a length. So you have 4 dimensions of length, x, y, z, and the ct, which is also lx. So you can use a meter or any unit of length. So we go back to our vector notation, to our 4-vector notation. So any x with a vector is a 4-vector. It belongs to a Minkowski space with 4 dimensions that are all transformed by the Lorentz transformation. So we have a new set of coordinates, not a new set of coordinates, but we should define to this set of coordinates, we should define our unit vectors. So any 4-vector x would be written as the sum from 1 to 4 or from 0 to 3 of x mu e mu. So x1 e1, x2 e2, etc. So x mu is the coordinate, is the length, the value of the coordinate, and e mu is the unit vector according to the direction time or x or y or z. So all these unit vectors e mu are orthogonal in a 4-dimensional space. So I don't know how to draw it on a screen in a 2-dimensional space. You have to imagine it. So these 4 unit vectors are perpendicular to each other. So it's the 90 degrees in a 4-dimensional space. So it's not a right angle. It's an angle. It's an angle between 2 curves, because now you don't have straight lines, you have curves. So I don't know how to draw it. no one knows how to draw it, so you have to imagine it. And you have E1, E2, 3 are the unit vectors of space, X, Y, and Z. And E0 is the unit vector that corresponds to the time axis. So as in a Euclidean space, when you multiply two unit vectors, so if they are orthogonal, if they are perpendicular, so E I times Ej is equal to 0 if I is different from J, and is equal to 1 if I equals to J, as in any normal Euclidean space or similar to any 3D space. So if you calculate the scalar product of two 4 vectors, x vector times y vector, so it's the sum of x mu e mu and the sum of y mu e mu, and or you can put mu prime, which means mu and mu prime are the same, so they all go from 1 to 4 or from 0 to 3. But we put mu prime just to say that when you fix one index here, you use it with the 4 indices of y. So when you say x0 e0, you multiply it by y0 e0 and by y1 e1, etc. You use the 4 coordinates. Then you switch to 1. x1 e1 should be multiplied by y1 e1, y2 e2, etc. Since if I different from J, the product is 0, so you will end up with the sum of x mu, y mu, the same mu. So it's x1, y1 plus x2, y2 plus x3, y3, etc. Which leads us to the square of a 4 vector. If you take the same vector x and you multiply it by x, so x times x is the sum from 0 to 3 of just x mu, x mu. So it's the sum of x mu squared. So it's x0 squared plus x1 squared plus x2 squared plus x3 squared. And if you put it in the Lorentz transformation, you will see that the scalar product is invariant. X times y is equal to x prime times y prime. We will see this in an exercise. So when we do exercises, we will calculate the scalar product of 2, 4 vectors. So why do we need invariance? Because we are physicists. We always need 4 vectors. You cannot make physical laws without invariance. If your quantity is not invariant, you cannot use it to make laws of physics. So if you are a physicist and you need to define a law of physics, you need to have invariant quantities. So put it in your mind and don't ever forget it, because you are physicists. So we always need invariant quantities to make physical laws. To make laws of physics, we need to have invariant quantities. So the consequence of this invariance is an invariance of the volume in space-time. If you calculate a volume in space-time, dv prime, a differential volume, and a small volume in r prime, let's say, which is the product of the 4 coordinates. So it's the x0 prime times the x1 prime times the x2 prime times the x3 prime. So if you replace in the frame R, you know that for the time coordinate you have a dilation, so you multiply by gamma. So you multiply by 1 over radical 1 minus v squared. So the dx0 prime is dx0 over the radical. dx1 prime, here you have a contraction of length. So you multiply by 1 over gamma, which is the radical of 1 minus v squared. dx1 times dx2, dx3, because you have no motion along y and z. So x2 and x3 will remain the same. So you see that you have a radical here and the radical here as the denominator. So you make a simple simplification by, so you reduce this radical, you end up with dx0 times dx1 times dx2 times dx3, which is equal to dv, the same volume in the frame up. So the volume is also an invariant, which means that the contraction of lengths and the dilation of time are done at the same rate. So you dilate your time as much as you contract your distance. So when you travel at the speed v, you are contracting your time by the same rate, you are dilating your time by the same rate as you are contracting your distances. So the total volume will stay the same. So you stretch your time by gamma and you contract your distance or your length by 1 over gamma. So you have no gamma left. You end up with the same volume in space-time. Volume is an invariant of space-time. So remember this. You stretch your time as much as you contract your length. So if you go back to the Lorentz transformation and you write it on in a 4-vector notation. So if you have this form of the Lorentz transformation, it's t equals t prime plus vx prime, or you can also use t prime equals t minus vx. If you take this form, t equals t prime plus vx prime, you replace t by x0. T by x0, so t prime is x0 prime. And you replace x by x1, so your x prime is x1 prime. So x0 is equal to x0 prime plus vx1 prime over the radical of 1 minus v squared. The same for x is x1, so x1 is equal to x prime, so now it's x1 prime plus v t prime is now x0 prime over the radical of 1 minus v squared. No motion along y and z, they stay the same. So y is equal to y prime, so x2 is equal to x2 prime. Z prime, so x3 is equal to x3 prime. So here in red is your Lorentz transformation and a 4-vector notation, or in a Zaminkowski space notation. You can put it in a matrix form using matrices, especially the Lorentz matrix, which is this matrix, gamma, gamma v, 0, 0, gamma v, gamma 0, 0, etc., 1, 1, and the rest are zeros. And you can take it from here. So from the set of Lorentz transformation, from the set of equations. So x0 as a function of x0 prime is 1 over radical, so it's gamma. x0 as a function of x1 prime, it's v over the radical, so it's gamma v. So you put gamma v. You don't have x2 prime here, so you put 0. You don't have x3 prime here, you put 0. The same for x1 as a function of x0 prime is v over radical, so it's gamma v. x1 as a function of x1 prime, it's 1 over radical, so it's gamma. no x2, no x3, so 0, 0. Here, x2 and x2 prime, so you have 0x0 prime, 0x1 prime, 1x2 prime, and 0x3 prime. Same for x3, 0x0 prime, 0x1 prime, 0x2 prime, and 1x3 prime. So this is called the Lorentz matrix. You can use it to define your Lorentz transformation as a matrix notation. So you can put the 4 Lorentz transformations or the 4 equations of the Lorentz transformation into this set of matrices. It's the matrix x0, x1, x2, x3, which is equal to the Lorentz matrix times x0 prime, x1 prime, x2 prime, x3 prime. So x0 is equal to gamma x0 prime plus gamma v x1 prime plus 0 x2 prime plus 0 x3 prime. x1 is equal to gamma v x0 prime plus gamma x1 prime plus 0 x2 prime plus 0 x3 prime. x2 is equal to only 1 x2 prime. x3 is only equal to 1 x3 prime. So this is the same Lorentz transformation put in the form of matrices. The same for the reverse transformation. When you have t prime is equal to t minus vx over the radical, so it's the same as x0 prime instead of t prime, which is equal to x0 instead of t minus v x1 instead of x. And x prime is equal to x minus vt over radical. So it's now x1 prime, which is equal to x1 minus vx0 over the radical. So you just replace x by x1 and t by x0. The prime will stay the same and everything else will stay the same. So x2 prime is equal to x2, x3 prime is equal to x3. Your Lorentz transformation as a matrix, x0 prime, x1 prime, x2 prime, x3 prime is equal to the Lorentz matrix times x0, x1, x2, x3. So x0 prime is equal to gamma x0 minus gamma v x1 plus 0 x2 plus 0 x3. x1 prime is equal to minus gamma v x0 plus gamma x1 plus 0 x2 plus 0 x3. x2 prime is equal to 0 x0 plus 0 x1 plus 1 x2 plus 0 x3. x3 prime is equal to 0 x0 plus 0 x1 plus 0 x2 plus 1 x3. So these two forms are the matrix notation of the Lorentz transformation. Now I will give you some classification of space-time curves or space-time intervals. You know that your proper time, which is a distance, a trajectory in space-time, is also called the world line. Trajectories in 3D space, we call them trajectories. In a 4D space or in space-time, we call them world lines. So the world lines are the trajectories in space-time. If you take a piece of the trajectory, so the proper time in the frame R prime, if you take it as a proper time, the tau squared or the t prime squared, which is t squared minus x squared, it could be written as x0 squared minus x1 squared. Or if you use your the entire space x, y, and z, you can write it as x0 squared minus the sum of xi squared. So remember that xi goes from 1 to 3. I is used for the 3D space from 1 to 3. So it's minus x1 squared minus x2 squared minus x3 squared. Since you have this minus sign, then your quantity tau squared could have 3 signs. It could be positive as if this quantity is bigger than this. It could be negative as this quantity is bigger. And if both quantities are equal, your tau squared would be equal to 0. So we have 3 cases. Let's begin with the first case when tau squared is negative. So t squared minus x squared is negative. So you have t squared, which is bigger, you have x squared is bigger than t squared. So the equation is negative. It means that you have more space than time. You have more x than t. So what does it mean to have more space than time? It means that there is no possible relation between 2 points of this type or 2 events of this type. Even light, which is the fastest thing in this universe, could not go from point A to point B within the time t. So if you have a time t, your time t is not enough even for light to go from point A to point B. We use such curves to describe a length or dimensions of objects, etc. These curves are outside of the cone of light. So you have your cone of light. These events and these points where the proper time is negative, they are placed outside the cone of light. So if you have 2 points outside the cone of light, you need something faster than light to make a connection between A and B within a time t, which is impossible. So there is no relation. So when you see points outside of the cone, it means that you cannot connect these points within the time t. For example, 2 simultaneous events in a frame. So if they are simultaneous, so delta t is equal to 0. So delta x squared is equal to just minus x squared, which is a negative quantity. So your simultaneous event in your frame would not stay simultaneous in another inertial frame. This type of curves is called the space-like curve, or the space-like world line, or the space-like trajectory. Because you have more space than time, so you call it a space-like curve. If you take a second case where tau squared is bigger than 0, so this t squared is bigger than x squared. The total quantity is positive. So you have more time than space. Here you can connect point A and point B either by light or by anything that travels with a speed v. So if it has the time to connect A and B within the time t, so you are in this case where tau squared is positive. You can move so at speeds which are that are less than c. So your points are inside the cone of light. If you can connect them with something that travels with less than c, then you are inside the cone of light. For example, if two events are happening at the same point in a frame R, so delta x is 0, the x is 0. So your delta s squared is equal to t squared, which is a positive quantity. So you have more time than space, so you call these trajectories time-like trajectories or time-like world lines. And the third case is when tau squared is equal to 0. So you have as much time as space. T squared is equal to x squared. So you are in the case of light and just light. You are in the case where you are traveling at the speed of light, which is only possible for rays of light. So all the lines that form the cone of light are the lines where the proper time is 0. So as I told you last time, for light, the proper time is 0. So it does not age. Its proper time is always 0. So these lines, these curves, or these lines form the cone of light. Here we are talking of light-like trajectories, because the only thing that could have this tau squared equals 0 is light. So you are on the cone of light, which is only possible for light. So we call these trajectories light-like trajectories. Okay, I'll switch, or I will go back to 4 vectors. We saw the position 4 vectors. When I tell you the 4 vectors, t, x, y, and z, it's a position 4 vector that gives you the position of a point in space or the position of an object in space. Now, if this position is variable, and if your object is moving in space-time, so you can calculate the rate of variation of this position with time. That gives you the velocity. So the definition of velocity is the rate of displacement within time. So if you have a curve in space-time of a certain object moving at a speed v, etc., if you take this trajectory, you consider an elementary displacement delta x. So your delta x is a vector. In this case, it is a 4 vector that has 4 coordinates from 0 to 3. And if you take the tangent to the small displacement, this tangent would be the velocity, the 4 velocity. So as you know from classical mechanics, the tangent to the curve is always the velocity of the object. So a curve in space-time, you take the tangent in space-time. So this is not a real drawing of space-time. It is a tangent in space-time, so it gives you the velocity as compared to the 3-dimensional velocity, which is delta x over delta t. Now you cannot take delta x mu over delta t, because in a Minkowski space, in space-time, your delta t is not invariant. Delta t is variable. And you need to consider this variation delta x in terms of an invariant of time. So you cannot use delta t. Instead, we use delta tau, because the invariant of time is tau squared or delta tau squared, the square of the proper time. So tau is the real time, not t. T is variable. So you cannot consider a 4-dimensional velocity by dividing the displacement by delta t. You have to divide it by delta tau, which is the invariant of time. The invariant of time is delta tau squared, which is delta t squared minus delta x squared. So delta tau is the radical of this quantity, so it's the radical of delta t squared minus delta I squared. So our 4 velocity, we will call it the vector u, the 4 vector u that has 4 coordinates from 0 to 3. So the coordinates of this 4 velocity are u mu, u0, u1, u2, u3, which are equal to delta x mu over delta tau. So it's delta x0 over delta tau, delta x1 over delta tau, etc. As in a Euclidean space, the 3D velocity, the vector velocity v, is always dx over dt. The 3 coordinates from 1 to 3 are the vi's, which are equal to dxi over dt. So it's dx1 over dt, dx2 over dt, and dx3 over dt. The 4 velocity has 4 coordinates. So the u mu, the coordinates of the 4 velocity are dx mu over d tau. So the x0 over d tau, the x1 over d tau, 2 over d tau, the x3 over d tau. We have a 3D velocity v. We have a 4D velocity u. Let's try to find a relation between the 3D velocity and the 4 velocity. They shouldn't be independent. When you switch from a 3D space to a 4D space, you should have a certain relation between 3D quantities and 4D quantities. So let's find a relation between the 4 velocity u and the 3 velocity v. The coordinates vi, dxi over dt, you can multiply it by 1, or d mu or d tau over d tau, which is equal to 1. So if you multiply it by d tau over d tau, you get dxi over d tau times d tau over dt. dxi over d tau are the 3 coordinates of the 4 velocities, the spatial coordinates of the 4 velocity. u1, u2, u3, dx1 over d tau, dx2 over d tau, dx3 over d tau, times d mu over dt. So let's find this quantity d tau over dt. Here in this equation, you don't have any v0 and any u0. So here you have 3 quantities, 1, 2, 3. In order to find this quantity d mu over dt, let's use u0, which is by definition is dx0 over d tau. dx0 or x0 is t. So dx0 over d tau is dt over d tau. And you know that d tau is the radical of dt squared minus dx squared. So if you put your dt outside of the radical, so you have to divide the inside by dt squared. So you have dt times the radical of 1 minus dx squared over dt squared, which is dt, the radical of 1 minus v squared. So you always go back to this old radical of 1 minus v squared, because dx squared over dt squared, the 3 dx squared over dt squared are v squared. So d tau is dt radical 1 minus v squared. So now you can find d tau over dt or dt over d tau. So this u0, which is dt over d tau, taken from this equation, dt over d tau is equal to 1 over the radical of 1 minus v squared, which is gamma. So you find your old quantity gamma which is u0. So the time coordinate of the 4 velocity is just gamma, which is equal to dt over d tau, which means this is the rate of variation of proper time with respect to classical time. So dt over d tau is the variation of time t with respect to the variation of proper time tau. So u0 is the rate of variation of time when you go from r to r prime or from r prime to r, etc. It gives you the rate of change, the rate of variation of time. Of course, if v is very, very small with respect to c, so in classical velocities that are very negligible in front of c, your d tau over dt or dt over d tau becomes 1, because here v squared is the v squared over c squared. So it goes to 0. Your rate is 1, and you go back to Newton, where t and tau are the same. But for higher velocities, dt over d tau is not 1, so you have to consider the variation of time between two frames. So when you switch from r to r prime, you have to consider this variation of time. So vi is equal to ui d tau over dt. So d tau over dt is now the radical of 1 minus v squared. So the ui, the 3 spatial coordinates of the 4 velocity, are given as vi over the radical of 1 minus v squared, which is gamma vi. So ui, the coordinate of a 4 velocity, is equal to gamma times the coordinate of a 3 velocity. Here we are talking about spatial coordinates, 1, 2, and 3. u0 is just equal to gamma. So your 4 vector velocity is given as u0 is equal to gamma, and ui is equal to gamma vi. So for each point of space-time, you have a position vector x mu with 4 coordinates, and a 4 velocity u mu also with 4 coordinates. Your classical trajectory is now called a world line, which is a curve in space-time. If you take the square of ui, you take ui squared, it is vi squared over 1 minus v squared without the radical. And u0 squared is gamma squared, so it's 1 over 1 minus v squared. If you calculate, if you see here, it's 1 and it's v. If you make u0 squared minus ui squared, then you end up with this quantity, which is u squared, u0 squared minus ui squared. It's 1 over 1 minus v squared minus vi squared over 1 minus v squared. Vi squared, it's v1 squared plus vx squared plus vy squared plus vz squared. So it's v squared, the 3D v, so it's v. So v squared, so it's 1 minus v squared over 1 minus v squared, which is equal to 1. So u squared is equal to u0 squared minus ui squared. You always begin, when you take the norm of a 4 vector or the square of a vector, you take it in the form of a proper time. So you take the square of the time coordinates, the time coordinate minus the square of space coordinates. we will always use this, this convention. So time squared minus x squared. So your u squared is u0 squared minus ui squared, which is the norm of the square of your 4 vector, which is equal to 1. So you see that spatial coordinates and time coordinates are related. So there is a relation between time coordinate and spatial coordinates. You see that this quantity is equal to 1, which is positive. So you can say that it is a time-like vector because its square is positive. You can find this result in another way by just using the proper time, delta tau squared, which is equal to delta t squared minus delta x squared. If you divide by delta tau squared, so you will get 1, which is equal to delta t squared over delta tau squared, which is u0 squared, minus delta x squared over delta t squared, which is ui squared. So you find the same relation again, which is equal to 1. So all the coordinates, the 4 coordinates of the 4 velocity transforms the same way as the coordinates of a 4 vector. So it's a 4 vector by Lorentz, it's a 4 vector, it's a 4 velocity. The norm is 1, is u is the radical of 1, which is 1. It is positive, so it's a time-like vector. So 4 velocities are time-like vectors because their square, their proper time, or the norm, the square of the vector is positive. It's is equal to 1. So we have a time-like vector. Okay, so I will stop here, and next time we'll see for acceleration.